Welcome back to this course on electronic systems packaging. This is the third lecture in this particular course. So, I hope you have reviewed the 2 hours of this series. The first one, I have given a brief introduction to the objectives of this course, what this course will aim at and what the viewer or the student will benefit from. Secondly, I have started the introduction to systems packaging, and we have seen various topics during the last hour. What I will now do is give you a recap of the last 2 lectures, so that you are on page with my lecture series. The first one is we have seen introduction. The second one, we have seen the term called microsystems. So, I am introducing this term called microsystems because many products today come under this classification. Then we have seen under this various application areas, right. We have seen system configurations in the field of automobiles, consumer electronics, communications, military and so on. Then we have seen or defined briefly what a product is, right, and we have also seen what a system means. Today's context, using the term system becomes very important, because if you want to define a product, you have to define system functions. So, any design today in electronics packaging should be viewed at system level functions. So, we have seen system level functions. Then we have briefly seen the levels of packaging, right. We have seen terms like chip level packaging, we have seen the term called board level packaging and system level packaging, what it means. Of course, we are going to see these terms in much detail. Then we have seen market scenario, right. We have seen globally the impact of packaging on the economic growth of individual countries and market share in various application areas. We have also seen the growth of semiconductor industry, because if you talk about packages and packaging, the starting point is your device, chip or a bare die, how the die is going to be packaged. So, we need to be on page with the semiconductor industry today, and in that context we have seen roadmaps. I have been stressing this, that roadmaps are very essential today to understand the growth of semiconductor industry. Then we have seen the history of semiconductors. We have seen various processes over the last few decades, and then we have seen the impact of materials, processes and the direct impact on the evolution of systems. We have also seen a very important factor that dictates the roadmap, that also influences the growth of industries, and that is known as the Moore's law. I hope you can recollect what Moore's law is, which briefly states that the number of transistors built on a die doubles every 18 months, but I also mentioned that in today's context it actually the growth is around 24 months. But Moore's law is still valid today. We have seen that, and the roadmap of ITRS and other industries up to 2014, which I have shown in the last class, is a direct indication of the validity of Moore's law. Then we briefly talked about chip making process, chip making flow chart. Of course, I mentioned to you that we are going to look at a detailed process flow of how a chip is made. So, these are some of the things that we have seen in the last class. Now, today I will take you through the various application areas that I briefly mentioned in the first class. We will discuss some representative products in each of these areas, and we will also slowly get to a point where we can define what packaging is, so that with the background that we have over the last 2 hours, we are able to define what packaging is. So, if you look at this figure, of course, this figure is slightly old, in the sense that it is about 5 to 6 years old, but if you look at the percentages in each of these sectors, it is more or less valid. We look at it one by one. If you look at the overall picture, the major share comes from computer and business equipment. So, you can see the volume of business and the percentage of market share globally and revenues earned also. Then comes communication systems. Then comes very important consumer electronics, industrial and medical systems. This can be fairly large systems, and then we have specialized areas like military and automotive. Automotive is a very growing sector, that is packaging for automotive is in a phased growth, well defined, and the volume is small, but at the same time the consumer demands in automotive are also fairly complex. So, we will look at it one by one, all of these sectors. If you look at computers and business equipment, the representative products are calculators, desktop PCs, printers, notebooks, photocopiers, PDAs, workstations, servers, and high performance computers. So, some of the products are very common, used in virtually every office, home, and very essential product. So, you can see the volume of business in these areas are very large. So, if you look at representative products in communication, where you can see high growth and high volume, cellular, PC handsets, line cards, LAN cards, pagers, modems, fax machines, LAN switches, routers, main switches, cellular and PCS base stations. So, one thing that can be said about the entire scenario in communication products is that the cellular phone is the mascot of this wireless revolution. So, today if you talk about packaging in communication, everybody talks about the cellular phone. Then comes automotive electronics. In automotive electronics, as I said before, we have complex systems, because if you take a car for an example, an automobile, the space available for the electronics is very small. We talk about under the hood electronics. All the electronics has to be built under the hood in atmospheres or conditions where it is very harsh. So, you can say automotive electronics will deal with harsh environment. So, the packaging engineer or design engineers for systems and subsystems that work with automotive electronics need to be aware about the harsh environment that the system will have to work with reliably over a period of time. So, let us look at the representative products in automotive electronics or automotive electronic systems. The first thing is engine control and management systems, very important. Transmission controllers, cruise controllers. Today's cars come with auto cruise facility, and therefore, you need to control the speed of the automobile and give information to the navigator or the driver about the cruise control mechanism and safety regulations also. Braking controllers, very important, traction controllers, suspension controllers, steering controllers. You see, today new models of automotive cars are in the market today. Some cars come with as much as 50 to 55 microprocessors under the hood, distributed in various sections of the car or automobile. Now, all of these information have to be displayed to the navigator or the driver periodically, so that the journey is safe. All information about, for example, the condition of the 4 tires, the air pressure in the tires, for example, and the fuel management system information, all of these information need to be displayed on the dashboard of the car. So, today's consumer or the end user requires such information. So, this is a specialized requirement. Of course, there is a question of cost getting into it, and consumers do not really mind paying that. So, in every industry specializing in car manufacturing, they have very high end systems which have these facilities, and these are special requirements. Not all cars require this, but high end systems will need to have this, because there are consumers who require this. Other subsystems in the automotive electronic systems will be lighting, wipers, air conditioning and heating systems, electronic dashboard and mirrors, safety, convenience and entertainment systems. So, how do you manage all of these systems, keeping the electronic system small, at the same time gelling well with the mechanical parts of the automobile? And as you know, when a car is driven on the road, there is a lot of vibration. There can be roads which can be very not really flat. There can be conditions where the road is a desert, water. There can be instances where under the hood you have corrosive atmosphere because of air, dust, water and so on. So, we are looking at a system which is very complex, where our electronic package or system level boards perform reliably. This is an example, as you can see here in this figure. This is an example of the places or the locations where you will find electronics, and where the automobile manufacturers need to build systems which are reliable. For example, you can see information that is needed to be displayed on the dashboard about the shock absorber, about the emission control unit, safety regulations like airbags, they need to perform when there is an accident, and which affects the great impact cost on the car, which affects the passengers. So, safety is one thing. So, when you include electronic systems in automobiles, you look at safety. Then there are other situations which continuously need to be monitored. For example, automatic gearbox information, headlight sensor, distance sensing, and for example, if you have electronic information like GPRS, for example, when you are traveling long distance, you need to connect to wireless, connect to various service providers, and those information need to be displayed on the dashboard. So, these are some of the very important electronic subsystems built for automobiles today. For example, I will give you a very nice situation which can become a very important packaging problem. For example, if you want to monitor the air pressure of your tires continuously, okay, and displayed on to your dashboard. So, you need to have sensors that go into the tire. Okay. So, very small sensor that continuously measures the pressure in the tire and displays it onto your dashboard. These are all what you call not required for all cars or medium range cars or low range cars, but there is a segment that requires all of this information, but very soon you will see these things become routine manufacturing add-ons that you can expect. Now, if you look at the corrosive atmosphere that is there in the hood, as you can see, this is under the hood. If you can look at the picture, this is the front of the car, and you can see there can be various situations where your system or system level boards can be located, and you need to monitor various things like the volume of engine oil present, and while working the temperatures are denoted here. Engine, for example, has a surface temperature at the steel at the metal body 140 degrees, exhaust system is working exhibiting a temperature around 587 degrees centigrade. Engine compartment close to the engine is 120 C. Engine compartment remote from the engine is fairly better 105. Exterior around 70, and you can see that the road surface, the friction exhibited when the car is moving, it's around 66 degrees centigrade. So, you can see your systems have to perform under these conditions, and then when you have moisture, dust and other situations which can easily cause corrosion or situations that can lead to failure or reduce the reliability, then this is a big design test for manufacturers. So, when you do a design for such a system, you need to take into account all of these considerations. Therefore, the material choice becomes very important. So, you have to really carefully consider what kind of materials need to be used when you build, when you package an IC that is going to be used in an automobile under the hood application, and that particular packaged IC is going to be mounted on a substrate. So, you have to look at what kind of substrate you can use that can perform reliably over a period of time under these adverse or harsh conditions. Now, this figure probably is a bit too early, but I will try to explain how for such a automotive electronic system you have a situation where you have a system level board. This is a system level board where the individual ICs are packaged and mounted on a substrate. So, the first thing you have to worry about what kind of substrate you need to use. So, what I am giving is for automotive electronics an example. So, this similar case study can be extended to a communication system or a UPS system or an SMPS system and so on. So, we will deal with such case studies as we go on. So, for example, if you are using an IC which is of the classification called flip chip, how do you take care of it and how do you protect this IC when you mount this on a substrate that is going to be used for a automobile application? What kind of solder material you will use? What is the interconnect mechanism that you will use within the IC or also connecting the device to the substrate? Is it a wire bond or some other connection choice? So, is it a wire bond or some other connection choice? We are going to see that. Then during the process, have you taken care of cleaning residues that can possibly affect in terms of corrosion and so on? It can reduce the reliability of the board. So, what kind of package material you have used? If you are using an unpackaged chip on board, how do you protect it? So, these are all some situations that I am trying to give beforehand, which will be dealt with during the course of this lectures. So, we have seen now automotive electronics. Now, we are going to look at consumer electronics and some of the representative products. VCR, which is very outdated today, audio systems, these are all again shrinking today. You can recollect large audio systems and players that were present over the last 5 years, but today here again you have seen a large growth, and we have seen miniaturization, compactness, okay, and more ergonomical. By ergonomical, I mean the user friendliness, man to machine friendly design. So, a lot of industrial design also goes into this. So, upfront I would like to say that when a product is packaged, you also take care of industrial design, or you can say mechanical design. This is a very completely different topic, but very essential for product packaging. Okay. Now, we talk about other representative products, game systems, cartridges, watches, portable audio players, camcorders, cameras and so on. For example, if you take cameras or camcorders today, if you open up the system and see, you will see a very thin flexible substrate which houses all of your components and interconnected on that flexible substrate. Earlier days they were using very rigid devices. For example, this is a very rigid printed wiring board that you see here. Today people are using, this is a very rigid device. People are now moving into flexible devices. Why should we move to flexible devices? Because there is less space in the product and you can flex the entire board and house it in very small areas. Okay. So, that aids miniaturization. Okay. That is one of the essential features of small handheld products today. So, other products include smart cards, microwave ovens, TV sets and so on. For example, I will show you a smart card here. This is a smart card and you can see here a device. Okay. This is essentially seen in all plastic card devices which is used for money transaction today. So, this has got all inbuilt information about your money deposited here, how much you have withdrawn. It can be used for transport or any other consumer marketing or retail activity that you can do worldwide. So, these are all very important consumer electronic products today. So, as you can see, the performance here that we expect is typically not leading edge compared to a military or a space system or a subsystem, and reliability requirements are fairly relaxed because the cost is also need to be low. So, you can't invest a lot of money to get very high end performance and keep it at low cost. So, cost is usually the overriding criteria to decide what kind of design implementation in terms of expensive devices and materials that can be used for consumer electronics. It is usually produced in high volumes, and that is why we are able to keep the cost low. Now, we will go into another sector called the industrial and medical systems. As part of this pie here, as you can see, industrial and medical systems is about 11 to 12% updated figure of the global market system scenario. So, if you look at the representative products in industrial and medical systems, we talk about test and measuring devices and instruments that are used in medical care and industrial systems. These systems can be very large. Calibrators, process control systems, motor controls, UPS or SMPS systems, and NC controls, numerically controlled equipments, like in for example, if you have NC drilling machine for example, and various numerically controlled mechanical systems. Other products can be in the health sector, vision systems, robotics. You have seen that today medical surgery and medical care has evolved, and new products using robotic surgery, even online distant help based surgery is now being carried out. Hearing aids, ECGs, implants, medical imaging systems, all of these come under the medical care electronic systems. Of these, the important things that occupy very small area or very small size products is the implants, and these directly go into the patient's body. Okay. I have a particular example for you to show. You can see very small systems. For example, there is a pacemaker, okay, that regulates your or monitors your heart after surgery, or if there are certain conditions for some people which need to monitor the heartbeat and the condition of the heart regularly, then in some cases it needs to be implanted. So, these are devices that are implanted into the human system close to the location where it needs to be monitored, like your heart. Okay. So, the surgeon decides where to implant it depending on the size of the system and depending on the nature of the disease. Then this particular device, as you can see, because it is implanted, it needs to be monitored from outside regularly. So, the device is in the midst of various fluids, including blood and other body fluids that are in contact with your package or the device. So, as expected, you will have to think about, or the companies which market these will have to very seriously consider the materials that needs to be used for these devices that go into the human system, because it should not be affected by the fluids, various fluids that are present, and it should not chemically react, it should not dissolve. Okay. So, these are some of the very essential packaging requirements. So, as you can see now, you get a flavor about the consumer electronics, the automotive electronic systems, medical care and industrial systems all have very different preset requirements for packaging. Now, we will get into another area which is military electronic systems, and we will see some of the representative products. In military electronic systems, it depends, the market depends on very complex relationships between various, because the growth depends on the current situation of what kind of military build-up each nation requires. So, the important products in this sector will be mobile communications, fire control systems, missiles, avionics radar, satellite links, land based radar and communication systems. So, we have gone through the various application areas one by one, and we have seen the representative products that are currently being used. Among the list that I have given here could be various other systems that are not listed, and there can be a great variation between the size of products in each of these application areas. So, the products are the important things for users today, and the user dictates what kind of products they want. So, normally a survey is done by the companies to find out what is the interest of the user, and based on that survey, market survey and the user survey, the products are designed. So, it is very simple to accept this statement saying that the users are the reason for products. Users are not concerned with the internal details of the product. If you take a survey, they will say this is what I want. This particular system has to perform this function, because I have a system that does not perform that. I would like to see a system perform an advanced functionality. How is it designed? They are not worried. How is it manufactured? They are not worried. But as an engineer, you have to worry about this. And the user wants to use the products effectively for a long time. Obviously, when they buy a mobile phone for 5,000 rupees, they want to use it for at least 5 years reliably without service and repair. But this is the utmost concern for engineers and industry. So, we look at it from a different angle, the common man or the users look at it from a different angle, but effectively when you design a product, we also look at finally these end user concerns. So, as an engineer, you have to look at what system functionalities you can build, what are the features you can have, simplicity in understanding its use, ease of use and taking care of the product reliability, its features in comparison to the competing products. Obviously, you have to be a leader when an existing product is there in the market today. So, you have to add new features that are much better compared to the existing product of another company. After sales service, happiness and pride in owning and using the product, and above all the cost. Everybody wants low cost. So, as an engineer, can you build a low cost product with high performance? So, in a nutshell, I would like to say that in packaging, please remember this has to be a very important and a key word in the industry houses: low cost product, high performance, except as I said in some special cases. So, a simple view of an electronic product will be there will be system functions built. The system functions can be for example, analog, it can be digital, or it can be a mixed signal, or it can be high bandwidth system function, it can be RF, it can be optical. So, it depends. It can be a mixture of each of these depending on the application area. So, there will be a system architecture based on these system functions. Then there will be ICs and components that perform these system functions individually and together when connected. There will be system level packages, that is printed wiring boards, this is racks and enclosures. User interface, very important. For example, your LCD display, your touch screen, your buttons, all of these are user interfaces that connect or communicate instantly to your boards and racks, and then they perform the system functions. Software of course, is embedded, very important today in today's product, because without that it is going to be very difficult to get the type of display and graphics interface that normally most of us want in handheld products. So, examples of system functions will be the MIPS or flops of a computer, that is a system function. Millions of instructions per second, if you say for a computer, that means you have defined a system function, you have used a particular processor for that, and you have interconnected other devices around the main processor to get the desired system function, which in this case for example is a MIP, millions of instructions per second. Power capacity of a product, efficiency of power conversion, that means you have designed something to get, let us say 99% efficiency in power conversion. Cleanliness of its output. So, for example, it says that the noise level is very low here. The power density of an SMPS, okay. All of these are pertaining to a product called switched mode power supply. extended battery life of portable products, that is a system function. So, you would have spent a lot of time deciding what battery you will use and then how to extend the life of the battery by your associated electronics with your main board or main design. In the case of a cell phone, for example, it has to provide reliable communication. In the case of automobile engine controller, for example, it has to work reliably under adverse or harsh environmental conditions. Integrated circuits are the main elements of an electronic product. I hope you can appreciate that, because integrated circuits or ICs or active devices come in different flavors, different application areas, you have different ICs. So, when you design a main system level board, you will decide what type of ICs need to be used for a particular electronic product and how to among a group of ICs, which one to select based on reliability and testability. So, these are the main elements of an electronic product. It enables us to build the required functionality into the product, as I said before. It can be analog, it can be digital, or it can be mixed signal and so on, or it can be analog to digital conversion, digital to analog conversion and so on. ICs can be available off the shelf or built as ASICs. Now, you can also custom build a group of ICs together and package them together to get a custom built IC set, chipset. A product also requires passive components. This is very important, because if you open up any product today and see, you will see that it not only consists only of the active devices, it also requires passive devices. So, what are the passive devices? Resistors, capacitors and inductors in some cases. So, resistors and capacitors obviously are required for most of the electronic products to control your active devices when it is powered up, and it is used as filters and so on. Electrical and electromechanical components are also required, for example, switches, connectors, cables, jumper wires and so on, right. So, if you look at any electronic product, your cell phone for example, they have switches, membrane switches, and they have connectors which connect the board to the display, for example, LCD. There can be 2 or 3 different boards in a system, and each of them are connected by connectors. So, you have to decide what type of connectors you have to use, what is the material contact there, whether it is gold or some other material that can provide very good contact without losing the electrical performance. Cables, if you want to connect a board to a rack of a system for example, and so on. A product also requires cooling components, for example, fans and heat sinks. You would have seen in personal computers, desktop, fans are being used to remove heat as quickly as possible when the device is powered up from the active surface of the IC. You do not want the heat to be built up. If heat is built, heat is built up on the surface for a long time, then there are problems with the active device itself. Heat sinks are used to remove heat. If fans are not used, in some cases heat sinks are used. So, you have to look at what kind of material choice you need to use if you are using a heat sink. Is it aluminum or is it some other metal? Then you have magnetic and optical storage system. Optical interconnects are today being used between 2 devices. For example, if this is IC 1 and if this is IC 2, normally you have connectors or conductors that is normally copper, but today people are looking at how to interconnect these 2 devices by optical methods, so that the signals are clear, there is no loss in signal propagation, and there is less delay in signal propagation, as well as we also look at other various electrical issues that are normally presented when you use a metallic conductor. Batteries obviously very important today. This is now part of the system. Batteries are part of the system today, and people are looking at how to integrate batteries into systems very effectively, and display components, as I mentioned, LEDs, LCDs and so on. So, you now got a fairly good idea about what a product means, what are the essential requirement for a product from an engineer's perspective after understanding the consumer's requirement. So, given this background today, I have now reached a point where I can define for you what is electronics packaging. So, it has taken some while for me to really give you a basis or a basic information about product, system and so on. Now, it is the time to define what is electronics packaging. It is very difficult to actually find a textbook information about electronics packaging, but we will see how best we can define, and I have taken it from various sources. A simple example or a simple definition for electronics packaging will be is the science and art of providing a suitable environment to the electronic product as a whole to perform reliably over a period of time. So, when you use the word suitable environment, it includes thermal, electrical and other green issues, and you can see the important word saying reliably over a period of time, very important for a product. So, when you say reliability, it has to perform, electrical reliability should be built in, thermal reliability should be built in, and the major functions of electronics packaging would be efficient signal distribution, efficient power distribution, efficient heat dissipation or cooling of the system or the device, and good protection including mechanical, chemical, electromagnetic. So, here we are going to look at EMI, electromagnetic interference or electromagnetic compatibility of the system. So, electromagnetic interferences are always there when a system is powered up. So, you have to look at how you can protect a system from these electromagnetic interferences, and the package must perform at the specified performance level. So, when you build a product, you give a data sheet or information about what are the specifications of a product, and the consumer should be able to realize this specification at any point of time when the product is functioning. Okay. So, if you look at this picture here, it relates to the basic points that I have mentioned here: signal distribution across the board, across the system efficiently between devices, power distribution from one system or subsystem to the other, which defines the product, heat dissipation. If there is an IC here and if you want to remove heat, let us say 10 watts, how efficiently are you going to remove this heat? Are you going to use a heat sink, or are you going to use a fan or some other method of cooling? What kind of materials you will use so that heat transfer is efficient? Package protection. So, are you going to use an inorganic package protection or an organic package protection, so that your system stays reliably? So, other definitions for electronic packaging, which again I have collected from various sources, I would like to put it here: the process of assembling a group of discrete electronic circuit elements into an electronic assembled device. We are not including semiconductor packaging or the manufacturing of ICs, or the semiconductor processing is never included in this electronics packaging device. So, as I said before in the first class, what is packaging? If this is an IC that is built and if you have a system here, so anything that happens between the IC and the system is packaging. We normally tend to ignore the wafer to the IC. This is actually not included in the definition for packaging. anything or all activity from the IC to the system, which includes packaging individual ICs and so on. Okay. So, this definition somewhat says in relationship to this definition that I mentioned here, that a group of discrete circuit elements, that is a group of IC, transistor, resistor, capacitor, electromechanical device joined together efficiently into an electronic assembled device, which performs system functions. The other definition that I have brought here is specifically the grouping or combining or combination of components which include integrated circuits or chips into an unit and through holes on a multi-layer circuit board. This talks about second level packaging or board level packaging, we will see that later, with subsequent attachment of the above items onto the printed wiring board. So, here we talk about packaged devices, here we talk about second level packaging on which the packaged devices are mounted, and finally, it also involves taking a concept of a circuit design and making a finished circuit. So, everything starts from a circuit design, like your VLSI CAD, how you start with a VLSI activity to get a particular wafer and a chip. Here we talk about a circuit design or CAD for a printed wiring board, and you talk about how efficiently these can be managed on a substrate, whether it is an organic or inorganic substrate, and how a system function can be built on that substrate and eventually integrated into the enclosure. So, other definitions as I continue. So, if you look at any encyclopedia or the web, I have used the term electronic systems packaging very often because it defines the complete system. There can be other terms like electronics assembly, electronic component packaging, electronics assembly process, or simply electronics packaging. They are all synonymous with the term electronics packaging. Okay. I hope you can follow this. The process of converting a circuit schematic design, so we talk about design, into a manufacturable electronic or assembly unit, very important statement. You can't make a circuit design that is not manufacturable. It has to have all the thoughts gone into whether it can be manufactured or not. If you make a design that is not manufacturable, your precious time and money of making a design process is waste, and it should be of high performance, cost effective, which I mentioned and I have stressed a number of times here, highly reliable, easily testable. This is something that I want to introduce, easily testable. We do not want to make a system that once it is manufactured you can't test it, very difficult to test it. Okay. And then you have to look at issues that can sustain the external environment of the system. That can be temperature, that is what temperature it is going to work, what is the location, whether it is an dusty area or a desert or a hill station where it is going to work, moisture, dust, infrared radiation, vibration shock, fatigue failure, etc., for a reasonable period of time. There can be certain application areas like space electronics, for example, where they look at this parameter, vibration shock, as a very important phenomenon that is always built into the design activity. So, the process shall also follow the principles of DFM, that is design for manufacturability, then design for reliability and design for testability. As an engineer today, I think you must remember these keywords DFM, DFR and DFT, because in current industry situation there is a lot of interaction between designers and manufacturing people. In earlier cases about a decade ago, this interaction was completely absent. Today an efficient product is created because designers talk with manufacturers, designers talk with test engineers, and designers talk with reliability engineers, so that they can evolve a very nice design that can be manufactured. Now we come to a slide where I am going to define levels of packaging. So, level 0, if we can call this, it is interconnections on the monolithic silicon die, that is your VLSI activity, and level 1 is packaging silicon dies into single chip modules. Or single chip packages. You can call it as SCM, single chip modules. So, here as you can see, it is called level 0 because it really does not come into the realm of electronic systems packaging, because as packaging engineers we need to know the silicon process definitely, but we are taking the die and then looking at packaging options. So, this is up to the wafer build. Okay. And from the wafer it is singulated into single chip modules. Then we have multi chip modules based on chipset technologies. For example, you can build a multi chip module which is abbreviated as MCM. You can take a group of ICs together, IC 1, IC 2, IC 3, and interconnect them on a single substrate or a common substrate, and then interconnect them to form a multi chip module. So, the individual ICs 1, 2 and 3 can come from different companies. It can perform different system functions. So, one can be an analog IC, one can be a digital IC, one can be for example, a memory IC. Okay. So, these can be interconnected to form a multi chip module. This will have its own set of IOs, input output pins, and they can be mounted as a single chip module onto a substrate, organic or inorganic. Then we have printed wiring cards or printed wiring boards, and then the level 4 is called the complete system. It will consist of several sub assemblies which are interconnected by connectors. Okay. It can be connected by wires in some cases, and finally, this system will go into a mechanical enclosure. So, that is part of the mechanical design, that is part of the industrial design activity. So, what I will try to show now is, in the earlier class I have showed you what a wafer is. Now, we have defined or understood what level 1 is, and what is level 1? It is a single chip module. Now, this is a single chip module, this is called a DIP package, this is a single chip module. If you rip open this and see inside, you will see a bare die interconnected to the leads that you have seen here on the outside. Okay, these are the IOs. So, this is a single chip module. Now, another single chip module is here, but the configuration is somewhat different compared to this. This is again a single chip module, it contains one IC inside. Okay. Now, typically if you look at this device here, this contains a group of 4 unpackaged die, bare die you can see, and these are interconnected on a common substrate, and this can be packaged like this device. It can be packaged with the encapsulant here, and this will have its own set of IOs, and this will be a multi chip module. In this case, there are 4 die or dies that are interconnected on a common substrate. I will also show you a very advanced single chip module. You can see a bare die on a simple substrate, and then on the other side you will see solder balls which represent the input output pins of the device. So, since this contains only one chip, this is called a single chip module. Okay. And I have shown this sample before. This is again a Intel Pentium processor, and this is a input in the form of a pins. So, typically if you open up and see, this can contain a single chip or multi chip module depending on the functionality built. Now, I want to show you an unpackaged die. If we can look at the, this is a 1 rupee coin, and I want to show you the size of a unpackaged die. You can see the kind of integration that has been built into a bare die. Typically such dies are packaged in the form of a quad flat pack like this, and then the input output leads are built so that you can handle them. So, as we go along in this series, you are going to see different types of packages that are going to be built, and we will also see current package. For example, this is a chip size package. Again, I am putting it close to the 1 rupee coin. You can see this is a very small device, but packaged, whereas here you see unpackaged die, this is a packaged die. So, a packaged die which is almost the same size of a unpackaged die, how it performs, what are the criteria or what are the situations when you can use an unpackaged die and when you need to package it, are some of the issues that we will be looking at. So, this figure represents what we have just discussed. So, from wafer to level 1, level 2 multi chip module, level 3 printed circuit board, level 3 is a set of cards which forms the motherboard on the motherboard, and level 4 is your system. Your system can be a mobile phone, it can be a PC, it can be a laptop, it can be a camcorder, whatever. Okay. So, in PCB printed circuit board, we are going to look at various technologies like through hole technology, surface mount technology, direct chip attach methodology, and there will be opportunities for me to show some tutorials on and some video clips on each of these technologies. So, here please remember wafer size, very important, that dictates the cost of the semiconductor manufacturing. As you know, we are in the 450 mm silicon wafer dia. Okay. Wafer fab cost I have indicated in the last class, something like $2.7 billion to set up a wafer fab, and the die size from the wafer depends on what kind of package you want to make and the number of IOs that you want, whether it is going to be 600 IOs or 4000 IOs and so on, and what kind of technology we will use to package this single chip module. This is a single chip module, whether you are going to use a solder ball interconnect technology or you are going to use simple pins, okay, as input output leads. So, I will stop here for this particular hour, and basically what we have seen in this hour today is we have seen the entire sector of packaging, different application areas. We have seen the individual representative products in each of these areas. We have defined what electronics packaging is. So, this will give you an idea about the activities in electronic systems packaging, leave alone the semiconductor packaging. Then we have tried to look at what are the levels of packaging, level 0, 1, 2, 3 and 4, and we have also seen some representative samples as I have shown here in the display. In the next class, we will look at again various examples in the various levels of packaging and try to look at some case studies. As a packaging engineer, what you need to look at in terms of when you start designing a product. That will be in the next hour. Thank you.